Hi, so now comes the more difficult part of the continuity lemma, which is going to be a bit involved. To prove this other direction, we need to do some more tricks. So what are we proving first? So we're going to assume that we have these generating functions, these integer distributions. They all have generating functions. We're going to assume that the generating functions converge somewhere. We don't know where, but they converge somewhere for every s between 0 and 1. From there, we're going to prove that the mass functions have a limit, and then if we build this generating function out of that limit, that's exactly where the generating functions converge to. Okay, so this is the task to do. Assume convergence of the generating functions, and from that show the convergence of the mass function, and show that the limit of the generating functions will satisfy this with the limit of the mass functions. That's what we need to do. This is going to follow something called a diagonal argument. And it's a very interesting one. And it's something we are going to see one more time in the, oops, now you can see it. And it's something we're going to see one more time in the unit later on. So it's called the diagonal argument. And first of all, let me abbreviate the abbreviation. I'm going to define Pn of k as an abbreviation for the probability that xn is equal to k. Okay, and what I want to show is that for every k, this has a limit. And then that limit has something to do with the limiting generating function. Okay, so here is what I'm going to do. I'm going to list the mass function for x1. Okay, the mass function for, the mass function for at k equals to 1. So x1 is going to be here actually, and x2 will be here, and x3 there, and so on and so on. And so P1 at k equals to 0 will be at this position. I'm just going to draw a big table of these values. P of 2, so this is for x2 at k equals to 0. K equals to 0, n equals to 2. K equals to 0, n equals to 3. So the mass function of x3 at 0. The mass function of x4 at 0. The mass function of x5 at 0. And so on. Let me do one more. Okay, so these are the mass function values, and they keep going at k equals to 0. And then I'm going to put down the mass function values at k equals to 1, n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, n equals to 6 at k equals to 1. Okay, and then let me do a few more. Mass function of n equals to 1 at 2, mass function n equals to 2 at 2, 3 at 2, n equals to 4 at 2, 5 at 2, 6 at 2, and so on and so on. So this is k equals to 2, and I'm going to do one more. P1 of 3, P2 of 3, P3 of 3, P4 of 3, yep, P5 at 3, P6 at 3, and so on and so on. K equals to 3, and it keeps going. Okay, so now these numbers are all between 0 and 1, right? These are all probabilities. These are the mass function values. So they are all in 0, 1. Any sequence in 0, 1 will have a convergent subsequence. Any sequence in 0, 1 will have a convergent subsequence. So maybe this guy, and then this guy, and this form a convergent subsequence, and they will converge to somewhere. Okay, they will have some limit, which I'm going to call, no, I'm not going to call this anything for now, but they have a convergent subsequence. Okay, so what I'm going to do is I'm going to forget everything that I didn't pick, but not only in the first row, but in every row. In every single row, I'm going to forget everything that I didn't pick in the first row. Now the remaining numbers in the second row will have a convergent subsequence. In particular, I'm not very much interested in P1 because I want to make at least one step, but maybe these guys form again a convergent subsequence. So they converge somewhere because they are numbers between 0 and 1 in a compact interval. Every sequence of numbers in a compact interval will have a convergent subsequence. The ones I didn't pick, I immediately forget. And not only in that row, but in all of the rows. And then I'm going to pick this guy and some more people which will have a convergent subsequence, which will form a convergent subsequence that goes to some limit. And here as well, I'm going to forget everything I didn't pick. Everything I didn't pick, I forget. And out of the remaining numbers, I again have a convergent subsequence, and so on and so on. Okay, subsequence. Okay, so that is what I'm going to do. Okay, so now I'm going to pick now a particular subsequence. So I'm going to take the first of the first row, the second of the thing from the second row, the third of the third row, and so on and so on. So there is not enough space here to draw everything, but so here's my first, second, third, and fourth member of the subsequence. So I'm going to pick the fourth of that row, and so on and so on. So that's gonna be my sequence I pick. So pick the first subsequence member in the first row, pick the second subsequence member in the second row, the third subsequence member in the third row, and so on and so on. Okay, that is going to be a subsequence. So my subsequence is going to be, so that I'm going to call n prime. It's going to be 1 for this one. It's going to be 6 for that 6. It's going to be whatever number I see here, maybe 10. And then here it's going to be maybe 15, and so on and so on. That is a subsequence. Okay? Now, here's the point. Number 1, number 6, number 10, and number 15 are all members of my first row subsequence. The reason is that I forgot everything that was not selected in the first row. So anything I picked underneath must have been selected in the first row. So 1, 6, 10, 15, and so on are all members of the first row subsequence. 6, 10, 15, and so on from this are all members in the second row of my subsequence. Okay? And then 10, 15, and so on are all members in the third row of my subsequence. So this one here, this subsequence n prime, is eventually, after some initial non-agreements, eventually will become part of each of the subsequences. Each individual subsequence will contain this one eventually. Okay? So therefore, the mass function at each row, what are the rows? The rows are the k's. So for every row, in other words, in every k, the mass function of n prime for that k has a limit, converges as along this subsequence here. That's because if I fix k, then I fix a particular row, and in that particular row, this subsequence will be eventually will be part of that particular subsequence which converges to a limit here. Okay? So these limiting values will just sit here. The limit for k equals to 0 of this guy is the 1 here. The limit for k equals to 1 for this guy is the 1 there, and so on and so on and so on. So I made a convergent subsequence of mass functions. I made a convergent subsequence of mass functions that converges for every k at the same time. Okay? This is going to be a particular mass function. Okay. Now I can build up from this mass function a generating function. Pn prime of s is defined to be the sum as k is summed from 0 to infinity of this mass function times s to the k. So I am having some generating functions along a subsequence n prime, which for example could be 1, 6, 10, 15 and so on. And this is a subsequence of generating functions. Okay, however, my assumption was that I do have convergence of the generating functions. Okay, so this is, in fact, I don't even need to do a new notation. In fact, what I'm having here is really p of xn prime, because I'm using the mass function for n prime. These are all mass functions of my original random variables, which I assume they have some mass functions. I didn't know that they have a limit, but along this subsequence they do, and along this subsequence I can construct the generating function. Okay. However, this will be a subsequence. This thing is a subsequence of pxn, the original generating functions, because n prime is a subsequence of n. Okay, this is a subsequence of pxn, and this thing converges because if pxn converges by assumption, that's what we assume, that pxn s converges to ps. That's the assumption we made, right? The limit of the generating functions exists, and this ps. So by assumption we have a convergence here. Therefore, every subsequence converges there as well. So we know that it follows from here that along this subsequence we also have convergence of the generating functions. This is also equal to, in the limit, p of s. Okay? So what do we have so far? We produced a convergent subsequence of mass functions. We considered the convergent, the corresponding subsequence of generating functions, and because we have a convergence of the generating functions, we know that this thing converges to p of s. Okay. Now, suppose, now comes a little bit more of an abstract argument. Suppose that we have another subsequence. If n double prime is also a subsequence, such that the mass function values converge again for every k, as n prime, n double prime, as n double prime goes to infinity. Suppose that we have another convergent subsequence like that, then the same argument holds, and then the same argument holds. The limit as n double prime goes to infinity, P of x and double prime exists and is equal to P of s. Okay? So now comes the final piece of the argument. So what we know so far is that we have some subsequence that converges. Okay, so what we know so far is that we have some subsequence of mass functions p n prime that converges, that has a limit as n prime goes to infinity, a subsequential limit. Let's call this limit p prime of k. Let's assume that there is another subsequence, n double prime. So let's assume that there is another subsequence, p n double prime, that again converges along another subsequence to something I call p double prime of k. Again, a subsequential convergence. Okay? And now comes the first part. Now comes the previous video. The previous video said that if we have convergence of the mass functions and we produce the generating function out of the limit, then there is convergence of the generating functions. Okay? So if we produce now a generating function out of this p prime, which I'm going to call p prime s, sum k goes from 0 to infinity, p prime k s to the k. So that's the generating function produced from the limit of the p primes. And we're going to produce the generating function out of the p double primes, sum from 0 to infinity, p double prime k s to the k. From part 1, from the first part, or from this direction, okay, from this direction, we know that the limit of the generating functions for x n double prime must be this limiting generating function for the double prime sequence, and we also know that the limit of the generating functions for x n prime must be this generating function produced out of the limits. However, the bottom of the previous part was that these limits exist and they are equal to ps both. And that's because we assumed, in the direction we are proving, we assumed that the generating functions exist, the limit of the generating functions exists. So it doesn't matter which subsequence we take, both of these people must be p of s. Okay? Now if p double prime of s is equal to p of s and p prime of s is equal to p of s, then of course these people must be equal. Okay, that's a triviality. However, the generating functions are unique. The generating functions are unique for a distribution. And this follows, it follows from here that the mass functions, if the generating functions agree, then these guys must also agree. If the generating functions p prime and p double prime agree, then by uniqueness of the generating functions, we conclude that p prime of k, which this thing is made of, so these mass functions must be equal to p double prime of k, which that thing is made of. And so what we proved so far is that, first of all, we have a convergent subsequence, okay? And we proved that if we have another one, then they have the same limit. Okay, if we have two convergent subsequences, they have the same limit. Whenever there is a convergent subsequence, they have the same limit. Then there is an abstract theorem of analysis that if every subsequence converges to the same limit, then the original sequence converges. So it follows, that's an abstract theorem in analysis. If every subsequence converges to the same limit, then it follows that the original sequence P of n of k converges to that same limit, P prime of k, which is equal to P double prime of k. And if we produce a generating function from that limit, that is going to be P of s, which was the limit of, that is going to, so okay, let me write this out. So and from the first part again, convergence of the mass functions means that the generating functions converge. So therefore, the generating function P xn of s must converge to either P prime of s or P double prime of s, and both of those is equal to P of s. Okay? So to summarize again, we proved that there is a convergent subsequence of the mass functions Pn prime k that converges for every k at the same time. If there is another one, Pn double prime k, that also converges somewhere, we don't know where, then because of part 1 and because the generating functions are unique and they have a definite limit by assumption, it follows that these two limits must be the same. If these two limits are the same, then for every subsequence we have the same, every convergent subsequence we have the same limit, then the original sequence converges, and so then P and k converges to P prime of k or P double prime of k for every k. And then due to the uniqueness of generating functions and due to the convergence of generating functions, the limit of the generating functions made by this mass function must be the same as the generating function made by the limit by the previous part of the theorem. So that concludes the proof. We now proved everything we needed to.